Good morning. Today we're going to be discussing the brainstem and the cerebellum. What problems do they solve and how do they solve them? We're not going to be discussing the details about how the neurons implement those solutions. I just hope to explain to you the basic operating principles behind these two brain structures, starting with the brainstem and then moving on to the cerebellum. Okay, so one of the really important things that the brainstem and the cerebellum do is they allow you to control your body, as in the angles of all of your joints, your movements, and your pose. And to illustrate the challenges involved with this seemingly easy everyday task, consider, for example, this fox that's carrying an egg in its mouth. Now, foxes, they do this all of the time. They raid the hen house and they steal an egg in their mouth and they run off into the forest and then they bury the egg in the ground. And then in the dead of winter, when they're cold and hungry, they come back and they dig up the egg and they eat their tasty treat. But how does the fox carry this egg in its mouth without crushing it or dropping it? This is a surprisingly difficult task, just to hold something in your mouth like this, to safely carry a delicate and valuable object. Now, naively, you might think that you, as a smart human with a big brain, could, build a mathematical model of this physical system. I mean, you understand physics, right? We understand that the muscles contract and that puts a lot of forces on the lower jawbone to hold it up. And we understand that the egg has momentum and weight, and we need to counteract that momentum and weight with the force on the jaw to hold the egg inside the mouth. I could start writing some equations on the board to describe this physics problem. But actually, we can not model this with equations. This is far beyond what anyone could ever model mathematically. The difficulties are everywhere, and they mostly stem from the fact that the real world is a very messy place. The real world is full of unpredictable bumps and disturbances. Take, for example, the muscles in the jaw. The muscles, they get tired and they get fatigued over time due to depleting oxygen and glucose levels. And as a consequence, they produce less force until, of course, you rest up for a moment and they recover their original strength. You can feel that lactic acid burn when you use your muscles too much. Muscles also can get damaged due to the normal wear and tear of using them. You know, like when you exercise or work out. And with good nutrition, the muscles will grow back stronger. But if you exercise without eating enough protein, then they might eventually heal, but they'll be weaker than before. And the sensory organs that tell the fox how hard it's clamping down on this egg, some of those sensory organs are stochastic, and some of them have highly non-linear response properties, which add to the challenge of building any kind of mathematical model of this system. Another challenge is that the physical properties of this egg are unknown. You won't know how heavy the egg is until you pick it up. And you don't know the angular momentum of the egg either, which is important if the fox ever turns its head. You might assume that it's a normal object with a uniform density, but actually the egg is filled with two different types of free-floating liquids, which really screws with any calculations that you're trying to run here. So building any kind of mathematical model of an egg ahead of time is very difficult. And another difficulty with holding this egg is the fact that the fox's own movements jostle its whole head up and down. As it runs, the head bobs up and down, and that imparts a lot of different forces on the egg that the fox needs to counteract in order to keep the egg in the mouth, but not counteract too vigorously, or else it'll crush the egg. And this is an inanimate object. Now imagine that instead of a non-moving egg, imagine that this was a baby and the baby is wiggling around its limbs and you're trying to hold the baby without dropping it, but you have to counteract the random momentum of the baby wiggling around so that you don't drop the baby. So clearly this is a difficult task, even though we take this skill for granted. Okay, so the way that the brain controls the body is by using a principle called closed-loop control. also known as feedback control. Closed-loop control is a guiding principle throughout the whole central nervous system, and I've drawn a diagram of it here on the board. Closed-loop control is a method of getting to a desired place in the world, known as the set point, and it does this by comparing the set point with the sensory feedback, which is coming from the nerve endings in your body, and that tells you where you are in the real world. So the controller compares what you want to see in the world with what you actually see in the world, and you basically just subtract these two things, and the result is an error or deviation, and that tells you what to do. The sign of the error tells you which direction to move in, and the magnitude of the error tells you how far to move in that direction. And this error signal gets sent to the muscles, which should move you closer to where you want to be. In our example of the fox holding the egg, the brain controls the muscles on the lower jawbone with the goal of obtaining a desired level of force, velocity, and position, which is the set point, and there are sensory organs embedded inside of those muscles on the jaw, and those sensory organs measure each of those quantities, the force, velocity, and the angle of the jaw, and that's the sensory feedback. And by simply subtracting the set point and the sensory feedback, the brain can determine if it should relax the jaw muscles or pull on them harder. And closed-loop controllers, in general, they work very well. They update the motor command every time they receive a new sensory feedback, which means that they're able to react very quickly to unexpected disturbances. As soon as it detects an unexpected disturbance, it right away will update a new motor command that accounts for that sensory disturbance. And the controller can also be very simple in its design. The controller can basically just subtract the set point and the feedback, and it will just work. The controller, it really doesn't care about the exact value that it's sending to the muscle. It just modulates the output in whichever direction it needs to achieve the desired set point. It doesn't calculate some plan far out into the future. It just reacts on a moment-to-moment basis. However, one of the downsides of closed-loop control is that it can get stuck in an oscillatory feedback loop. What happens is that the controller overreacts to some disturbance or mistake, and that overcorrection leads to another larger mistake. And once that happens, they can get stuck in a loop. Think of someone with shaky hands. Like, imagine that I'm trying to hold my hand, like, at this height. Like, this is the set point. And I move my hand up towards the set point too fast. So when it reaches the set point, my hand has too much momentum to stop, and it ends up above the set point. And then the controller says, oh, we need to move down. And it pushes it down, but once again, with too much force. And so you end up back where you started. And then you just bounce back and forth across the set point, but you have too much force, so you never stop at the set point. That is what I mean when I say you get stuck in an oscillatory feedback loop. Now, all of this may seem too simple, but trust me, it gets more complicated. Because the brain doesn't just have a closed-loop controller, it has many closed-loop controllers. It has a plethora of controllers scattered throughout the brainstem and into the spinal cord. If you have multiple sensory inputs, then you can control each sensory input individually, and then you can combine all of those controllers together to control all of the sensory inputs at once in a scheme known as Cascade Control. Each distinct sensory input is going to have its own controller and its own set point dedicated to it. And the controllers are connected to each other by connecting the motor commands out of one controller into the set point of another controller. In this way, they can form a hierarchy of controllers, with the higher tier controllers controlling the set points of the lower tiers, and only the lowest tier of controllers actually sends its commands to the muscles. Cascade Control allows the controllers to operate somewhat independently of each other, and each controller can be designed and tuned to operate in its own little domain very effectively, but also still communicate with the other controllers. Cascade Control allows many relatively simple controllers to work together to create more complex behaviors. For example, to control a simple skeletal muscle like the jaw in our example of a fox holding an egg in its mouth will involve these 3 levels of controllers for the position of the muscle, the level of contraction of the muscle, the velocity of the muscle, how fast it's moving, and the amount of force that the muscle is applying. And they're connected up as shown here. So when the animal wants to change the position of their jaw, they control the set point of the position controller, and the position controller then says, I need to move. And the way you move is with velocity. And so the position controller sends its commands to the velocity controller's set point. The position controller does not talk directly to the muscle. The position controller talks to the velocity controller. And the velocity controller, well, when you want to change your velocity, you need to accelerate. And to accelerate, you need to apply a force. And so when you want to increase the velocity, you need to apply force, and there is a force controller for doing that. So the velocity controller doesn't talk to the muscles either. The velocity controller sends its commands to the set point of the force controller. And the force controller talks to the muscles. The force controller at the very bottom of this hierarchy is what actually makes the muscles contract until the muscles say, hey, I've reached this level of force, and the force controller subtracts that against the set point to determine if it needs to apply more force or less. So in this way, you can start with a command for the position, and you can also control the velocity and the force, and all 3 of those sensory measurements are going to be combined in a sensible way to control the final result. You can control each of these things individually, but also when you try and control the high-tier controllers, it's gonna use the lower-tier controllers as well. Something to notice here is that the derivative of position is velocity, and the derivative of velocity is acceleration. And of course, acceleration is directly proportional to force. So each of these controllers is acting on the derivative of the quantity that they measure and control. So that's Cascade Control in a nutshell, but Cascade Control can get more complicated than this. This here is just a linear chain of controllers, but it actually does form a whole hierarchy, where you can have a high-level controller controlling multiple low-level controllers, and you can have a low-level controller that's being controlled by multiple different high-level controllers. And you can end up in situations that seem like they should come into conflict. The multiple controllers don't all work together, and they may not find a solution that's copacetic to all of them, but usually they can. For example, if you are lifting your leg up and putting it down, there are controllers involved with making sure that your leg is high enough up that you don't trip on things as you're walking over them. But there's also a controller that makes sure that your body is upright, and that controller wants your legs to be underneath you on the ground. So you have these 2 controllers that are both acting on the shared set of leg muscles. And that can make your leg twist into some rather strange positions, but as long as, both controllers end up satisfied at the end of the day, then you won't trip on things and you won't fall over. Okay, now let's talk about the cerebellum. In the 1970s, 3 scientists named David Marr, Masao Ito, and James Albus each independently discovered that the cerebellum uses supervised learning to implement an associative memory. Now let's unpack what those words mean. An associative memory is a device that stores pairs of input and output values, and when it's presented with a known input, it will return the associated output value. Supervised learning is a class of learning algorithm in which an external supervisor or teacher signal provides the correct answer for the algorithm to learn from. The inputs to the cerebellum are the current sensory inputs, what you're seeing right now, and the current motor commands, the actions that you're in the middle of doing. Together, these 2 inputs are called the sensory motor context. And the cerebellum, it associates the sensory motor context with some value that the supervisor gives to it. And then the next time you're in that exact same sensory motor context, the cerebellum will automatically output the value that the supervisor previously gave to it in that context. The cerebellum can memorize a vast number of these associations between sensory motor contexts and supervised outputs. It has an enormous number of cells in it to do this, but it is in essence a very large lookup table where you look up the current sensory motor context and you get out some value that was previously written into it by the supervisor signal. Ever since these discoveries more than 50 years ago, scientists have been wondering, what is the cerebellum storing? What do its mysterious outputs represent? And finally, let's talk about what the cerebellum is actually doing and how it helps the brain. This schematic diagram shows the cerebellum and a closed-loop controller connected together. The cerebellum implements a forward internal model. What that means is that it analyzes the animal's current sensory motor context in order to predict what sensory inputs the animal is going to see in the immediate future, what is about to happen. The closed-loop controller then uses those future predicted sensory inputs as an additional source of sensory feedback about the actions that it's in the middle of doing. In essence, the cerebellum gives the controller a preview of what its actions are going to do. If the controller makes a mistake, then the cerebellum informs the controller of its mistake, and the controller can start issuing corrections immediately without waiting for sensory confirmation that it made a mistake. For some tasks, by the time you get sensory feedback about a mistake that you've made, it's already too late to fix that mistake. Closed-loop control is entirely reactive, and so it's incapable of solving tasks like that on its own. But the cerebellum can tell you that you're making a mistake as you're making it before it's too late to fix it. And so the closed-loop controller can start correcting its mistake without waiting immediately. The brain can go through many of these cycles of predictions and corrections as the action is unfolding. This works because the cerebellum is very, very fast. The cerebellum is faster than the real world. The real world might take between 100 and 200 milliseconds between when you issue a motor command. It has to travel from your brain, down your spinal cord, out into your limbs, into the muscles which contract, and then your body interacts with the world, and then the external world pushes on your sensory nerve endings, and that sends feedback all the way back up into your brain, and that can take quite some time. In the case of eye movements, it can take easily 200 milliseconds between when you issue a motor command to move your eye to look at something and when you get visual confirmation of the thing that you're now looking at. If you're trying to look at a fast-moving object, 200 milliseconds is a long time to wait to see if you even looked in the right place. But the cerebellum will give you sensory feedback after about 10 milliseconds, which is way quicker than the real world could ever return sensory feedback. So that's the gist of how the cerebellum helps you. Now let's analyze this diagram for a moment. The cerebellum now participates in two different feedback loops. We have one feedback loop through the real world with our 100 to 200 milliseconds of latency, and then we have this other feedback loop through the cerebellum, and that one bypasses the real world and instead uses a predictive model of the real world. And the closed-loop controller can just treat these two feedback loops as basically just the same. It doesn't really care that it's getting sensory inputs from two different places. It just cares that both sources of sensory feedback are timely and accurate, and preferably both. Although the real world is accurate but not timely, and the cerebellum is timely because it's a prediction of the future, but it might not be accurate because it is a prediction. Because the cerebellum operates so quickly, the brain can operate quickly as well. The brain can move with much more force and more speed without accidentally overshooting its targets and entering into those unstable oscillations, because the cerebellum operates faster than those oscillations. But to take full advantage of this, the controller needs to be tuned with a very high gain in order to produce those high velocity movements. And then you have a controller that is ill-suited to work without a cerebellum, because the controller is tuned to move fast and it's requiring the fast sensory feedback from the cerebellum. And then if your cerebellum gets damaged or disabled, then the controller will almost certainly enter into those unstable oscillations. As an example of this, alcohol temporarily disables the cerebellum. The cerebellum is affected by a much lower level of alcohol than the rest of the brain, and that's why people who've had a drink or two, they might still be able to think, and they might still be able to carry on a conversation, but their cerebellum is not working at 100%, and so their hands shake, and they lose some of their fine motor skills. The cerebellum is not limited to modeling your body either. The cerebellum predicts your future sensory inputs from all of your sensory modalities, not just the proprioception measurements from the sensors embedded in your muscles, but also the tactile sensations that you feel are predicted by the cerebellum, and all of the things that you hear with your ears are predicted by the cerebellum, and all of the things that you see with your eyes are also predicted by the cerebellum. And all of those other sensory modalities, they make use of this same basic architecture and these same basic operating principles. For example, the cerebellum, it predicts what sounds you will hear with your ears, including the sound of your own voice, and this allows you to accurately control the sounds that you make by, the movements of your mouth and tongue and vocal cords. This is also why people who've had small amounts of alcohol, which once again disables the cerebellum, causes people to slur their speech a little bit. Another example of your cerebellum helping you to control unexpected things is the skill known as hand-eye coordination. For example, hitting a baseball with a baseball bat, which requires controlling the position and the velocity of the baseball bat in 3 dimensions. Not your hands, but the tip of the bat where you're going to hit the ball is what you're trying to control. And the cerebellum and the brainstem make no distinction between your hands and the tools that you're holding. For the purpose of controlling them, it's all using the same basic principles. Another interesting thing about the forward internal model hypothesis of the cerebellum is that it's very easy to understand how the cerebellum can learn this internal model in the first place. The cerebellum learns as long as you're awake. It's receiving a steady stream of sensory and motor inputs to base its predictions off of, and there is a supervisor in the cerebellum which checks all of the predictions that the cerebellum makes. It simply waits a fraction of a second to see what actually happens, and then when the cerebellum's predictions are wrong, then the supervisor will issue a correction for the cerebellum to learn from, and that is how the cerebellum is able to perform supervised learning of an associative memory. Coincidentally, in 1957, a man named Otto Smith invented something called the Smith Predictor, which combines closed-loop control with forward models in a remarkably similar way as the combined brainstem and cerebellum. The Smith Predictor uses forward models to predict both the future sensory input as well as the length of the sensory motor delay, which they needed in order to differentiate between unwanted disturbances and the intended effects of a motor commands. The Smith Predictor was invented in order to control industrial processes, which have long delays in the sensory motor feedback loop. However, for safety reasons, this idea never took off. Dangerous industrial equipment needs to work correctly the first time and every time afterwards without fail, or else it's gonna get someone killed. It is dangerous after all. Industrial applications cannot incorporate learning algorithms. That's just not a thing they can do. The forward model was expected to be engineered ahead of time. But as we saw when we tried to write equations to simply hold an egg up, making forward models by hand is very difficult and error-prone, and that really limited the usefulness of the Smith Predictor for its intended application. On the other hand, animals, unlike industrial equipment, can fail over and over again until we learn that forward model correctly. For example, when infants are first learning to walk, they fall over several thousand times before they succeed. When animals are playing in a safe environment, their cerebellum is learning in preparation for when they grow up and move out into the dangerous real world. But industrial equipment does not have a playtime. When you're doing a jigsaw puzzle, it really helps to look at the big picture on the back of the box that it came in. My goal with this lecture was to show you one possible big picture, so that when you're studying all of the details about the brain, you can start to see how they all might fit together. I'd like to emphasize the word possible, though. Throughout this lecture, I've been careful to say the word hypothesis and not theory. The difference is that a theory is widely accepted as the truth and is supported by a whole lot of evidence. A hypothesis is merely an idea that could be a theory one day, but is still under investigation. Since this is an abstract conceptual framework, it's actually quite hard to prove that this is the absolute correct way that the brain works. It's not like a concrete fact where you can prove that it is the way that it is. So take it with a grain of salt that there are other competing hypotheses. Regardless, I hope you've learned something interesting, and until next time, meow.